This is one of the core lectures of the course. It's on safety and risk. They're sort of mirror images of each other. The safety problem creates all kinds of issues. And if anybody asks you, what is engineering ethics, a good, brief elevator answer is, well, it's how to deal with safety and the fact that we can never design a truly safe system. That's really a very fundamental problem. You'll see that it is impossible to make something perfectly safe. If you spend more money, you can usually make it safer and safer, but then the public isn't going to buy your extremely safe product because it costs too much money, okay, like an extremely safe car. Okay, so there's this delicate balance that you have to go for that sort of makes it safe enough, okay, so you don't get in trouble with the law, like, okay, or NHTSA, the National Highway Traffic Safety Administration, but maybe not too safe because it will cost too much and people then won't buy your product. So some cars, companies get away with having safer cars and people buy them because they are safer. Could you name a car company that has one of the better safety records? Anyone? Volvo. That's the classic answer. They tend to be big, heavier cars, or not big cars always, but heavy cars. And they survive crashes well. And they also have certain higher reliability in parts of them. So with respect to safety and risk, I got a kick out of this cartoon, so I'm going to share it with you. That's a suck there on the left. He says, Wally, I discovered a deadly safety flaw in our product. Who should I inform? No one. The stock would plunge and we'd have massive layoffs. Your career would be ruined. But my negligence could cause the deaths of a dozen customers. The first dozen's always the hardest. Isn't that Wally for you? Okay, so the engineer's concern for safety. We demand safe products. When I say we, of course, engineers want their products to be safe, obviously. But we, as speaking with respect to the public, also want products to be safe because we are going to use those products. What we have to realize, however, is that you have to pay for safety. And engineers that, for instance, design automobiles or other nuclear power plant control systems, etc., know that very well. But the public does not know it very well. They sort of think, well, they were negligent, the engineers were negligent, they made this unsafe. Well, no, you didn't, weren't willing to pay the money to have the safety that we knew how to put in the system. So there becomes this sort of conflict between your professional knowledge of how to make something safe versus the public's general perception of safety and who's at fault. The other problem is that individual engineers make these decisions, and what may be safe enough for you may not be for others. You may go out on the weekends and go jumping out of airplanes and all kinds of things, and you think, oh, this product's safe enough. Okay, so there is that sort of a problem. Or, on the other hand, some engineers are very risk averse. They want something that's extremely safe, becomes too safe in terms of the expense, and they run into problems. Typically, marketing people say, come on, we got to make this product cheaper. Okay, so there'll be a conflict there. So what we have to accept, though, is that absolute safety is not attainable or affordable. A good example, back in 92, I don't know if you remember the San Francisco earthquake. It was quite a significant earthquake in the Bay Area. And I don't know if you remember the 880 bridge. They call it a bridge, but it's sort of more of an overpass. So what it is it's a double-decker highway that travels for a long period of time over businesses and housing areas and so forth. So when this earthquake happens, this was terrible. A lot of people were killed. The top layer fell onto the bottom layer of the road, where the cars were driving, actually, and then it all fell all the way to the ground. So the people on the bottom, the bottom road, I mean, there was cars in there just squished. People were just squished. It was terrible. Okay, a lot of people died. And of course, everybody starts screaming at the civil engineers. Why didn't you make this bridge safe? We have earthquakes in California, and they go, hold on a minute. 2 years ago, we told you this bridge was unsafe because we've gotten additional data on earthquakes. We knew there was a problem, and we proposed to do a fix to it, which basically involved taking these large metal straps and sheets and wrapping it around the pillars that held the bridge up. Hugely expensive. So they had to use a levy, okay, a tax levy. And guess what? The public voted the tax levy down. So they just came back and said, look, you guys voted it down. It's not our fault. We knew there was a problem. Okay? So this is a great example of how, money impacts safety. Okay? The engineers in that situation knew full well that it was just a matter of time before the next earthquake came. Now, the way these civil engineers do these designs, you think, well, why don't they know already how to design for an earthquake? Well, the way they do these designs for earthquakes, they do the following. They build a bridge in a computer, and they simulate it in the computer, and they run earthquake data through the simulation. But they only have earthquake data for a certain number of past years, and it has a certain frequency and amplitude. Okay? So they did those designs, deployed the bridge. A couple years later, they get new data, and they're like, holy cow, this earthquake's different. It's fundamentally different than what we've gathered data on in the past. And that's why they did the redesign. They said, look, we need to fix this problem. Okay? So this gives a good example how, the engineers that put the bridge together in the first place were fully competent. They can't be blamed for these deaths. Okay? The engineers that did the redesign were fully competent. Now, there may have been some marketing problems trying to get people to pay the taxes to get the thing fixed, but nonetheless, it didn't happen. Okay? So let's talk a little bit about what we mean by safety, like how do we assess safety. We could use this earlier capabilities approach of Amartya Sen that I talked about a few lectures ago. Okay, so these are a little dry. A thing is safe if were its risks fully known, those risks would be judged acceptable by a reasonable person in light of the settled value principles, whatever that means. Or a thing is safe to a certain degree with respect to a given person or group at a given time if, were they fully aware of its risks, they would judge those risks to be acceptable to a certain degree. So this whole degree thing of safety is really quite important, okay? We're used to thinking about degrees of safety, right? Just in someone's driving patterns, you could think of the degree of safety with how their driving behavior is, okay? Now, there's all kinds of safety issues with respect to relative safety. Safety for an engineering prototype versus a released product. Of course, if you've got a prototype, you've dreamt up a new product, you're working on it in your lab, you don't worry about safety very much because there's just a few people in the lab and you inform them all, be careful with this. Okay, no problem. That's a very different situation than after it's gone through manufacturing out into the public. Then it's going to encounter all kinds of people, as you know from the idea of engineering and social experimentation. And then that's sort of where the rubber meets the road because there can be all kinds of safety problems. Another thing that a number of you will encounter is the issue of safety on a manufacturing line. How many people have sort of worked on or near manufacturing lines? Please raise your hands. Yeah, so it's quite a few of you. Maybe some of you are familiar with there's all kinds of different standards and laws like OSHA. There's all kinds of safety requirements. When you walk in some of these manufacturing areas, they'll require you to put on goggles or a hard hat and so forth. You're going to be coming across, many of you will come across this sort of situation. And that safety on a manufacturing line has a number of special features that engineers have to pay attention to, but often, guess what? You're going to be the people that sort of design for safety on the manufacturing line. And you're the people that will have to try to talk to that burly union person that isn't going to listen to your stupid safety advice, and you're going to have to figure out how to get them to listen to you. Okay, they're not going to listen to you college people. You don't know anything about the real world, and you hear this sort of comments. Okay, and so it takes not just technical skill, but some personal finesse in the end. Now, risk. So risk is the potential that something unwanted and harmful may occur. So there's experimental risk associated with introducing a new technology, just like we talked about with social experimentation. One example that I'm quite familiar with is this Toyota Prius example. I own a Toyota Prius. It's about 5 years old, and it's fascinating. The darn thing. So you put it in reverse, and it only uses the electric motor to reverse. There's no engine driving it in reverse. So it's extremely quiet, of course. Okay? And people, don't like jump out of the way if you make a mistake. You know, when you're driving, when you're backing up. This has become a problem. The other problem is that, I don't know if you're familiar with the Prius, when it first takes off from a red light, it has a problem, and one of the ways it saves energy is that it doesn't turn on the engine right away. Okay? If you press the accelerator just a little bit, it'll take off under electric power, and so it's quiet. Correspondingly, when you come to a stoplight, if you hit your brakes hard, it uses regenerative braking, so it takes that energy and turns it in, charges via a generator or the battery. It shuts the engine off before you get to the light. So there's this problem. It's right here in Columbus. People are trying to solve this problem with deaf people and the Prius because they can't hear them taking off and arriving at stoplights. They're used to hearing cars with their nice loud engine. Okay, so the Prius is fantastic. I mean, it gets 50 miles a gallon. It's a pretty good ecological car to some extent, at least. Yes.
Blind people.
Yeah, it's deaf people, blind people. I should add blind. Yeah, sorry. Was that what you were going to say too? Yeah, thanks. So this exposes a trade-off that wasn't probably thought of, and that is the environment safety trade-off. It may be helping the environment, but it's at the expense of the safety of individuals. There's often risk with the application of familiar technology. A classic example is anti-skid braking systems. So in my lifetime, these were invented and first deployed. When they first came out, of course, it was the fancy cars that had ABS, and no one else had it. So so they looked at the accident data that came in on these, and they were, optimistic. They were thinking they were going to help save a lot of people. Well, the problem was the cars that had ABS would indeed had a lower incidence of front-end collisions. Okay? Clearly. Problem, their number of rear-end collisions went up. They didn't get near the gain because other people didn't have ABS. They were just ramming them in the back. Okay? When they were stopping so fast, nobody else could stop that fast. Okay? So they didn't really realize the gain. I don't know what the data looks like these days. There's ABS is on a whole lot of cars now. There's always a remaining risk from trying to make a system more safe. And there's the acceptability of risk, the willingness to be subjected to risk. People don't have as much a problem with subjecting themselves to risk as the typical pattern. They're much less willing to be involuntarily subjected to risk. Some people would ask if risks on the job are voluntary, what about a manufacturing job? You could say, you're taking this risk by operating around this robot, around these chemicals, your problem. You chose to work here, your problem. And that's typically not going to work in terms of your responsibilities as an engineer. You're going to have to try to take care of these people. You could say, well, you could just quit, but that's not always possible. If you talk to some of these people, if they're in a dangerous situation, often what happens is the company offers them additional pay additional compensation, and then they sign off on the health risks that might come from that dangerous situation. I've been around this. It's pretty. One of my first I did an internship early on, and there was an electronics manufacturing line, and there was a bunch of people that were working over top these. They call them solder bath, and it was just the solder was just melted and letting off all these fumes, and they're working right over top of them all day, every day of the week. Okay. Just terrible. I don't know if they got extra funds. They needed the job. So did I do something about it? Back then I had no idea how to do something about that. I was just a little intern. I wasn't running the show. Not making excuses, but maybe something should have been done. Next, if you have piecework based, that means if you pay someone by an amount of money that's proportional to the number of pieces they produce, that's piecework based. Sometimes workers behave less safely, and it creates a problem. That has to be monitored. So safety complaints from on the job always have to be listened to. When you people, there was quite a few of you that raised your hand at work on the manufacturing line. Some people will never complain. They're happy. It's nice. You chat with them, whatever. But other people, they're going to complain all the time, and you have to listen to that. Okay? Because if you don't, well, number one, there may be a safety problem. Somebody could really get hurt. Number two, if they get hurt, you're gonna get yourself in a big mess because they complain, and they may document that. Magnitude and proximity of risk. So what if you have personal connections with the victims? What if the person on the unsafe manufacturing line is your mother? Okay. What if you definitely know that the public will immediately include your spouse and children? It's a nice exercise to think about, rather than the person, you're working on that manufacturing line, you look at a situation, you're like, that doesn't look right, that looks unsafe. Think about it in the context of if that was, a spouse or close relative, you really want to get it right. That's how you should treat those people. These personal relationships, this is sometimes called a sense of solidarity with workers. You want to, if you're in that situation where you're in charge of safety on a manufacturing line, you really want to get to know the people that are being subjected to the unsafe situations. You want to talk to them, you want to get to know them socially, okay? Talk to them, learn about them. You develop a sense of solidarity, which is, in a sense, just means you care about them. You want to make sure that they're treated right and do not get injured. So what about work on a design project? If risk appears small and there are hints that may grow with time, be careful. We'll talk more about it, but the Challenger disaster that's covered in detail in the book is a fantastic example of where the problem was growing. Okay? They had problems with those O-rings a number of times. When the weather was cold, it was just a matter of time before it was cold enough that it would be a serious problem. Okay, so Roger Beaujolais, the engineer at Morton Thiokol, who was one of the key people in this, he knew this disaster was going to happen, essentially. I mean, when you look at the data isn't that complicated. Just read that book carefully a little bit and you'll be like, can you believe that NASA let that thing take off? I mean, it was unbelievably stupid. I mean, it's so clear it's unbelievable. And yet the engineers weren't able, Roger Beaujolais in particular, was not able to talk NASA into not launching. Just couldn't do it. Okay? He's talking all this technical stuff, and they're like, Roger, one guy said to him, his one boss, take off your technical hat and put on your manager's hat. And that was the big problem in the end. Lessons for the engineer. Problems with the public's conception of safety. The public is often over-optimistic with regard to familiar products that have not hurt them before and that they have control over. I know I had a friend once that was like this ABS thing, just loved it because he could stop so fast. And guess what he would do? He would drive wilder. Okay? So how much benefit did he get out of his safety system? Over pessimistic when accidents kill or maim large numbers or harm those that we know. The classic example is air travel. Air travel is like the safest mode of travel. Per miles traveled, number of people, etc. Okay, it's the way to go. But once there's a crash, there's a certain number of people who will never fly again in their life. Okay, that's just the way it is. So the real risk can be quite small, statistically speaking, at least. So for design considerations in terms of risk, absolute safety is not attainable, and improvements in safety often cost dollars. When I say often, it's almost always. We'll have some examples a little bit where it didn't really cost money, okay? But almost always it will. Products that are not safe incur secondary costs. You lose customer goodwill. If you make an unsafe product, people hear about the product hurting people and so forth. It degrades the reputation of the company. I mean, GM took a hit. The death toll due to their ignition switch problem went up last week to 23 people from 19, just when I talked last week. I mean, people are still being killed by that system from that. Okay? Warranty expenses on products are expensive, and those costs are passed on to the customer. It can hurt your market share, etc. Litigation costs, defending your company, for instance, or your engineers. The other secondary cost could be a business failure. There are times when companies actually just fail because they created an unsafe product and they really can't, survive anymore. What often though happens is the company just ends up with a bad climate, and their hiring potential goes down. You people, many of you, are looking for jobs either for internships or for companies. The reputation of your company, you're in a luxury situation because a lot of you will get more than one offer, and you'll be able to pick. And if one company has sort of a bad reputation, you won't pick them typically. Unless they offer you lots of money. But you typically won't pick them. So all these things, if your company's cranking out products that are unsafe, are going to adversely affect your company, which is ultimately going to adversely affect you if you're an engineer working for that company. So, a plot, actually, in an ethics class, okay? So this plot is pretty easy to understand. Let me go over it. On the horizontal axis, we have risk, some measure of risk. On the vertical axis, this is the cost to the manufacturer. Call it General Motors, call it whatever, okay? Now, there's 3 plots there. Let's pick P. P is the primary cost of the product, including safety measures. How much is the cost for the car, okay? Plus its anti-skid braking system on it. Well, if it is going to be a low-risk product, it's going to have high primary costs, okay? If, however, I'm willing to sell a product that is higher and higher risk, it will cost less and less money. Now, secondary costs. That's all that stuff I listed on the last slide. Okay, so warranties, things like that. Now, for warranties, litigation, etc., if I have a very low risk product, I won't be paying much out in warranties and litigation and so forth. However, if I have a high risk product, I'll be paying out a lot in that. So you see the curves in terms of your cost. As an engineer, when you do a cost analysis, you of course take into account not just the cost to put the car on the road, it's everything else associated with that, like the litigation or warranty costs. So if you add that up, you're going to add these 2 curves. That's this curve and this curve. Okay? Now, when I add those up, I get that curve up there at the top. It's got a nice dip down in it. Now, any good engineer, when they're doing a design, you're always trying to design to meet constraints, get functionality, and minimize costs. So that means you're going to try to minimize on that curve. Well, the min point is this point here, M. Okay? I'll give you minimum cost. That means, well, you spend a certain amount P to make sure it's safe, and it may be not enough to avoid some secondary costs, and you get your product, you put it out. The problem is that when the engineer does that analysis, typically they do it in a spreadsheet, right? Get everything balanced out, do the minimization, come out with minimal cost design. The problem is that the highest acceptable risk is usually back here. So you have to spend more money to get something that's safer. Because otherwise, if you're over here or further to the right, you're talking about trading off money for lives or money for injuries. And you're going to be too far towards the injury and death side, allowing more of those to occur so that you save your company money. Okay? So this becomes a problem, and usually in terms of engineering ethics, you want to be down here somewhere. It's not clear where. And the analysis would depend on every product. Okay? So lots of ethical issues arise. Next, knowledge of risk. Well, safety issues, even for standard products, are often not well understood. Well, the information is not shared between the industry. Ford and GM don't share information on ABS. They just wait till their first car comes off the line and then they tear it apart and figure out what they did. But they don't say, the Ford people don't say to the GM people, hey, look, we figured out how to make this a lot safer. Here, you can have this. There's always a new application of old technology, so we don't know what our products will encounter. Now, the problem is that uncertainties in design cause risk. We often use safety factors. Now, here's the Tacoma Narrows Bridge. Okay, I should probably put in a video. So, can you see what happened on this bridge? The Tacoma Narrows is up around Seattle area, and what you're doing is you're going over like an inlet from the sea and the ocean. And what happened on this bridge is wind started. It goes down through this Narrows, and it hits the bridge. And the wind was coming at a certain frequency. It would hit it, hit it, hit it. Guess what? It started to oscillate. The darn bridge started to oscillate. So it's moving like this, and then it just, boom, fell to pieces. So yeah, this is the lady's that was, I think this was taken from her video cam. Now, these crazy civil engineers, can't they do anything right? I mean, they needed to take into account the effects of the wind, but they didn't. Okay. Well, you certainly do now. Well, they learned their lesson. Now they have to design the bridge, run through the simulation of wind data that would correspond to the oscillations that would be induced here, and make sure the darn thing doesn't fall down. They rebuilt this bridge, by the way. You can look at it on the web. The problem is with this is it could happen again. And the reason it can happen again is there's uncertainties in materials. You don't know how strong a material is, for instance, such as the materials they use to construct the bridge. We have uncertainties as electrical engineers in the circuits we design. If those circuits are used in medical products, that can be a significant problem. What kind of uncertainty do we have? Well, one of them is that, you know what the silver gold band on a resistor means? It means plus or minus certain values in terms of what the resistance really is. Okay? When it says 22,000 ohms, it's not really 22,000 ohms. It's off by either, there's plus or minus 5% or 10% or 20%. And the resistors cost more, the less it's off. Okay. So the problem is that when the supplier tells you that their product will meet something plus or minus 10% or whatever, can you really trust it? Well, that can be a significant problem. Okay, so uncertainties in design end up creating risk. Here's another way to view this more abstractly, second plot. So here, what we have is stress on the horizontal axis, increasing amounts of stress on a product. On the vertical axis, I've got the probability of occurrence of a problem, a safety incident of some sort. Then I have the capability of the product. The capability shows this region here where it can cope with a certain amount of stress so well. In other words, if it has this amount of stress right here at C, it does the probability of occurrence that it can cope with the stress or has that capability is higher. In other words, it has its best capability up here. Now, the duty is, what is expected of the product, what you're subjecting the product to. And you expect a duty down in this region. Now, the problem is that on virtually all engineered products, there's an overlap in the middle. This is the problem case. That is where the capability may not exceed the duty. And if it doesn't, there's a high probability then of a failure, some type of an error. Okay. And this happens in not just mechanical systems or civil engineering systems, but electrical systems, etc. Problem is, do we know the capability and the duty? And the answer is no, not precisely. We have to estimate it. So there's a lot done in engineering. There's engineers that take on as a whole career just testing safety. Okay? You design tests with those comments above in mind, and you try to do accurate tests in trying to find the problem. Sometimes it's good to have like a design review board that looks at what you're doing to make sure what you're doing is safe. The other thing is you should be careful with the results of others' tests. Usually you don't want to just blindly trust others. As an engineer myself, when I look at my own error making, like if I make an error in writing a paper with one of my grad students, typically the probability that I make another error right in the same region is higher. It's kind of weird. I don't know. Maybe it's because I just wasn't thinking right, and I make one error, make another error, So if I find an error, I check really carefully in that whole region. It's the same thing if I lecture. If I'm on a board, if there's some problem, I make a mistake, man, I go back and make sure everything is really correct. So you as an engineer, often the hardest person to be critical of is yourself. And it's easy to ignore your own errors and own problems, but if you're doing safety testing, you got to be careful. You got to be very careful and being critical of yourself and others' work, and you have to invite others to be critical of your work. Okay? And you can't take it personally if you screwed something up. You got to get it right. Okay? So another problem is that testing cannot always be performed. Failures could be catastrophic. The example we had before is in some of these systems for nuclear systems, for instance, nuclear power plants. That's a good example. Sometimes the tests are just too expensive. Well, what we do in those cases, I can leave it to, the book talks a little bit more about this. They do a scenario analysis, so-called fault tree analysis. I'm not going to get into that. So, risk-benefit analysis, very common analysis done in engineering. So, it seeks to answer the question, is a product worth the risk connected to its use? Who benefits? Do they outweigh the risks? What's the environmental impact? Okay? When can you benefit from something and subject someone else to a risk? Usually, these things are kind of monitored quite carefully by laws. One of the problems here with the safety thing that safety engineers get into is how do you put a dollar value on human life? You're trying to determine how to cost out a car. Very complex thing to work out how much to charge for a car, right? You keep driving up the cost to make it safe because you're trying to, you're driving down the number of deaths, and it costs this much more $1 million to reduce one more death, or 5 more, or 100 more. And suddenly you have essentially a dollar value on death, right, of an individual. And that is really an uncomfortable situation to be in, but engineers are put in that situation all the time. Okay? when it comes to all these safety issues. The U.S. government uses typically a measure that values human life based on your earning potential for your profession. I've got some real ethical problems with that myself. Because that would say that, I don't know, chemical engineers make a little bit more than electrical engineers, so they're more valuable, fundamentally, as human beings, right? No, I think anybody would have problems with this. So engineers often supply facts for risk, so you have to be really careful. An example here is operator error and negligence are most often not the principal cause of accidents. Usually it's unsafe conditions. So in your view, for all of you that were working with people on the manufacturing floor, sometimes there's a tone that's set that says, oh, it's their fault. The safety stuff's all in place. It was their operator error. It's their fault. You better be really careful with that, because you got to set up an environment so that they won't make errors, essentially. So here's some examples of products that don't automatically increase costs. Okay, so you try to build the original design and embed safety. One of the best examples is the magnetic catch on a refrigerator. When I was a kid, the way they made a fridge is it had a latch, like lock type thing on it. So what was happening is little kids were getting in the fridge, closing the door, they were trapped. You couldn't push your way out of the fridge. And then somebody invented the magnetic latch. I mean, magnetic latch is really cool. You understand it's not the magnet that sucks it closed. The door is hung so that it falls closed. And then the magnetic thing is just there to snap it. Okay? It costs less money. Beautiful design. Okay? Some mechanical engineer came up with that, I'm sure. Ground fault interrupter. Significant safety. It's in all of your homes. You see them all the time. It's a cool little circuit design problem. Okay, as I'm sure saved tons of lives. Here's another motor reverse circuit that doesn't have any cost. So this is just an example of the technical design you can do. It won't cost any money, but you get safety out of it. Okay. So in A, what we have is, I have a battery. Okay, this is an easy circuit problem, okay, I promise you. You got a battery, and let's suppose that the switches are both down. Well, if that's the case, then this goes up through here, hits the polarity here, positive polarity on this side, negative polarity on this side, motor spins. Okay? Now, let's take this guy and pull them up. Well, what happens then is battery comes up here, positive polarity on the bottom, negative polarity on the top. What happens? Motor spins the other way, right? Motor spins one way or the other, depending on whether the switches are up or down. Nice and easy. But there's a safety problem. The safety problem is in the switch, the mechanical part. So what can happen is you could flip this baby and this baby won't flip. Now, let's look at what happens in that case. Let's say this guy stays here, this guy comes up here, goes around to here, whoop, you just shorted your battery. What happens to your battery? It gets hot, sometimes it'll blow up. Okay, starts fire, really bad, okay? Now, look at this little design. So this person, I don't know how they came up with this. This is really cool. So they took the battery and the motor and they swapped them. Okay? Simply swapped them. Now look what happens. Let's say they're down. Positive on positive. Negative on negative. Motor turns one way. Flip them both up. Now up here I've got negative up here. I've got positive down here. Motor turns the other way. Now let's do the interesting case for safety. Let's take this guy and leave him here, and let's take this guy and flip him up. So there's a mechanical failure in the switch. Look what happens. This guy comes up to here. Well, this guy comes around, around. What'd we do? We shorted out the motor. Who cares? It's a passive device. Okay? And the battery stays disconnected. Cool. So we short out the motor, nothing happens, it doesn't turn either way. We have a failure. It's a safe system, didn't cost a dime to redesign the circuit. Okay? Kind of a cool case. Okay. There's a so-called fail-safe and safe exit. Fail-safe systems, I don't see these anymore on the road. Back in my day when I was younger, they would have concealed headlights. So your headlights would, there would be these flaps that would close in front of them. And then when you turn on your lights, they would come up. So the fail-safe system would always, if there was a failure, it would come open so you could turn on your headlights. It wouldn't close while you're driving down the road in the middle of the night and cause an accident, okay? Elevators, question mark. A lot of elevators are fail-safe. At OSU, they're fail-unsafe, right? I mean, have you ever been in Dries Labs when the elevator fails? Well, it's horrible. That thing does all kinds of failure modes. I can give you some really, you probably think they're funny stories, but you know that those systems really are quite unsafe. Safe exits are important, for instance, at 3 Mile Island and Chernobyl. And I'm at the end. Now, I want to talk about this one a little bit, though. I want to leave you a little extra time, okay? So I wanted to finish a few minutes by design here. This is mock whistle blowing on safety. For those of you who have had a job in engineering industry, if you haven't, just write your name on a sheet. Bye-bye. If you had a job in engineering industry, have you encountered a moral dilemma or unethical practices with respect to safety? Please provide a brief description. Save descriptions of unprofessional behavior for later. Please do not use the names of companies or people's names. I'm not going to pursue cases. I've been asked that a number of times. They want me to go after their company. Wrong, I'm not doing that. This is for education only. Okay? You can use a separate sheet. If you don't want your name on the description of the safety problem, just put your name on a separate sheet, put the description of the safety problem